non-linear stuff to other opportunities, because I would say at this stage, the understanding the linear PDEs are actually much more important than the non-linear ones. Again, in the future, what you're going to see is that there's only a very small number. Only a very small number of types of nonlinear PDEs that can be exactly solved. And when people are facing different types of nonlinear PDEs, then people usually have to come up with completely different strategy. And there's no guarantee that there's a solution, nor there's any guarantee that let's say it's solvable or numerically safe. So, and also I believe that getting into the transform and distribution will be a very nice continuation of our discussion in chapter 5 about Fourier series. Okay? Because as we said, the Fourier series actually were introduced in a rather how to put it, in a manner that trying to getting rid of some of the, also sacrifice some of the mathematical rigor, okay, to make sure it's more absorbable at this stage for this class. Okay, so yes, so I suppose there will be one more homework. There will be one more homework for for chapter 6 and for chapter 7 and for chapter 12. So that's my plan. Okay, so again, let's now come to 6.3 Poisson's order. And so today, what we are going to discuss how to solve the Dirichlet quadratic problem. Okay, for a circle. So specifically, we're talking about the 2D Laplace equation, okay, which is uxx plus uyy equals to 0. Okay. For, let's say, for x squared plus y squared is smaller than a squared, and u exactly equals to h theta, okay, for x squared plus y squared exactly equals to a squared. So let me demonstrate what does that mean. So which means that we are investigating the Laplace equation, okay, first of all, a Dirichlet boundary problem of Laplace equation within a circle. Within a perfect circle, this is the origin. This is the origin. And therefore, under the polar coordinate, we will be able to relabel the boundary of the circle by the angle, right? So this is, which means that this is angle 0. This is angle 90 degrees, or let's say this is angle pi over 2. Okay, pi over 2. Okay, this is angle pi. This is angle 3 pi over 2. Okay. Something like that. So this is the following question. Okay, so this is the following question. If you are given the boundary of the harmonic function itself, okay, on the boundary, then can we solve? Okay, first of all, can we solve? Can we solve the harmonic function? Okay, from the Laplace equation? And but actually, you know what? Actually, before we really get started, actually, you see, we need to remind ourselves that the uniqueness. So first of all, there's no guarantee that there's a solution, right? Because when we were discussing the well-closeness of Poisson's equation and Laplace equation, actually we were stressing that we could actually easily prove the uniqueness of the solution using the maximum and minimum principle. However, actually we didn't discuss the existence and the stability of the solution. Okay, which means that there is no guarantee. Okay, so far there's no guarantee that we will have a solution. Okay? But of course, after we rightfully solve this equation, we're going to find that indeed there exists a solution, okay, which is called the Poisson's formula. In the case, okay, specifically in the case that for a predetermined circle, okay. But on the other hand, when we are getting into the Newman's condition, okay, which means that if I'm having not partial u partial x, but if we are looking into something like partial u partial n, okay, partial u partial n, which equals to, let's say, g theta. Okay, if we're looking into a boundary value problem like this, then actually what you're going to see is that there is not necessarily a solution. Okay, and such a point will be discussed in chapter 7.1. But at least the first 2/3 or half of this class for today is to solve. Okay, is to solve this equation. Is to solve the 2D Laplace equation. Okay, and considering a circle boundary value. Sorry, considering a circle boundary. Okay, so our method to do this, okay, is that since the boundary itself is a circle, okay, so it actually reminds us to utilize our knowledge of the polar coordinates. Okay, if we are able to first rewrite everything to the polar coordinates, don't forget that under the polar coordinate, my uxx plus uyy, okay, this guy exactly equals to urr, and then plus 1 over r, okay, ur, and then plus 1 over r squared, okay, u theta. Again, this is for what is the definition of theta? What is the domain for r and theta? Our r theta actually belongs to from 0 to a, okay, because a is the radius of the circle, okay, from 0 to a, and then multiply by from 0 to 2 pi, okay, from 0 to 2 pi. This is the domain for r and theta. Okay, this is the domain for r and theta. Now, based on our knowledge of partial differential equation, what do you propose to proceed? How do we solve a partial differential equation, a linear partial differential equation like this, when we not exactly know, for example, the source function, okay, or before we know anything about the analytical formula? What do you propose? Oh, okay. What have we proposed? What have we proposed? What did we do when we were trying to solve? We were trying to solve the wave equation, the heat equation, and later with some boundary value problems. What did we exactly do? Go ahead. Separation of variable, of course, that's one way. It is exactly the method I'm going to do today. But any other suggestions? Before we learn the separation of variables, how do we solve PDEs? Sorry? Core UV characteristic line. That's actually very tempting. But the question is, okay, so the characteristic lines are usually more suitable for one order 1, right? And so we use characteristic methods for what? For the for wave equation, okay? Before we introduce the separation of variables. But what do we exactly do before we implement the characteristic lines? So when we are having, what did we exactly do when we were trying to solve utt minus c squared uxx equals to 0? What did we exactly do at the very beginning? That was a factorization. Yeah. Factorization, right? Factorization. We found a way to factorize everything. Okay, so let's say here, it is actually something like ut minus c ux, okay, ut plus c ux equals to 0. So again, if we are able to use factorization, okay, if we are able to use the factorization, then we can actually reduce the order of a second order differential equation to first order differential equations. We are well known, we know very well how to solve first order differential equations, right? If they're first order, then actually it's nothing that's very horrible. However, you see, if we would like to use the factorization over here, assuming you see, utt minus c squared uxx, this is actually order 2 on t, order 2 on x. Here, we're having order 2 on r, order 2 on z. That actually seems very tempting for us to directly use the separation of our variables. Oh, sorry, for us to use the factorization, right? But actually, you know what? Why don't we try it? Why don't we spend about 2 or 3 minutes to see what will happen if we are really using? So can you find a way to complete the factorization? But just a little hint, well, not hint actually, a little reminder over here. The r over here is not a parameter. It's a variable. Okay, so when you are doing the factorization of operators, okay, you should be very careful of that, because here, if the c over here is switched to something like x or t, then you know how much trouble it may create, right? That means that the differentiation, okay, the differentiation should include these variables at first. Okay, so why don't you try about 2 or 3 minutes on that? I can tell you actually, I tried. There was one night when I was staying here, not here but in my office. I actually tried about 1 hour, okay, to proceed with the factorization, okay, to see if I could use the factorization to solve this type of PDE, okay, because ChatGPT told me that I couldn't do that, and I didn't quite believe the answer, so I made some attempt by myself, and okay, here I'm going to see what will happen.
我发现我们做到最后，如果用 x 和 y 的话，它搞成这样的一个东西，这算什么？
你们看呀。
Professor。
might have already
证明
noticed what's the biggest problem, and you don't have to spend another hour like I try to tackle these problems. So if you really want to do factorization, and well, factorization means that we are reducing an order 2 to order 1, right? Okay, then and that which means that here actually we need things like so you are certain parameter, certain parameter. Let me use a circle here, and then plus you sit up and another parameter, and then plus certain constant functions, Let's say
哦，三人 constant。
let me use this. Okay. And then again, UR plus U theta, and then plus certain constant functions. Okay. So
You think there's other parameters?
constant functions. So that's our factorization, right? This is our factorization. And our job is going to be determining what is this. So with it. Okay. And according to the outcome, we are having a UR. So that basically tells us that this guy, the product of these two terms, these two coefficients should be 1. Okay. And we are always sorry, not UR, but actually what I should do is like this. What I should do is actually, because this is the factorization of operators, so actually partial R, partial R, yes, partial zeta, partial R, partial zeta. Okay. So the product of these two things should be 1. And we may even simply assign them as 1, because we can always try to normalize one bracket with another. So these things are 1 for now. Okay, then now the problem still exists, right? The problem is still that, so first of all, I need to obtain a 1 over R squared of partial zeta. Okay. So now the question is, what should I assign over here? Okay, what should I assign over here and here? To obtain a 1 over R squared, you zeta. See, when we are doing the differentiation on the direction of zeta, it doesn't involve R, which means that and this is a parameter of R, which means that so this guy can be a function of R, and this guy can be a function of R, and it doesn't interfere with the order of the differentiation. Okay, that is not a problem. However, the problem is that actually we're not having any auxiliary term. We're not having any auxiliary term between R and theta, which means that we do have a U R zeta or lower U star. Which means that these two terms, because you see here, by doing a partial R and then something, a function of R, partial zeta, and something partial zeta, something partial R. After doing that, we should obtain something that's zero. The corresponding coefficient should be 0. The corresponding coefficient should be 0. And the trouble will start from that. Which means that even if you find a way, actually it's not even a problem. It's not even a problem for us to find appropriate coefficients over here and coefficients over here, for us to create an environment that we're having UR 1 over R squared U zeta, and we're having no auxiliary term. But you see, but after that, well, when we face our biggest problem, which is the 1 over R UR, what kind of differentiation can produce 1 over R UR? Well, you see, let's say so that means that first of all, because we are not having a constant term, right? We're not having a constant term, so everything over here is with at least one order of differentiation. So we can say that so these two big circles, there's only one over here. There's only one over here, and let's say we can. It's not harmful for us to assume that. Something like this. Okay, it's something like this. And then that means that there has to be a, you see, there has to be some certain term over here, right? There has to be certain term over here. Then, because we will have to create for whatever r you are. Okay. However, that will bring you right away something partial zeta, which is not over here in the original question. And by doing that, we will have to very carefully design what is in these coefficients. Okay, what are in these coefficients? Okay, to make sure that they cancel each other. Okay, and finally, we will find that by doing that, you are basically trying to solve another partial differential equation. Okay, by doing that, you'll be end up solving another partial differential equation. Okay, which might succeed. Okay, I don't know. Okay, because I gave up after spending the 1 hour trying to find the coefficients. But I mean, again, it might succeed. But I doubt how much does it, relieve our pressure. Okay, so this is my experience. Okay, with the factorization. Again, when is the best place for factorization? The best place for factorization is that there is no such things like this. Okay, all the coefficients are constants instead of functional variables. Okay, let me write it down over here. Factorization is best. Okay, best for differential operators. Okay, with constant coefficients. Okay, with constant coefficients. Not quite clear. Okay. Again, you may succeed. I don't know, but you may end up taking more time as I do. Okay. So this is my comment for and also a reminder for us to review some of the critical stuff. Okay. You may have another question. Why don't we simply proceed with the factorization of this? Right? The Poisson equation, or actually the Laplace equation, it doesn't have, indeed, it actually doesn't have any look, all the constants are coefficients, are constant. Oh, sorry, all the coefficients are constants. Right? All the coefficients are constants. 1 and 1. Can you factorize? Do you know how to factorize uxx and uy?
Partial
I, just I, right?
partial x plus I times
and
partial
then
y.
ux minus uy indeed, then you're going to succeed. Without any doubt, you're going to succeed. Do you want to provide an answer why we didn't use that in the previous lecture, especially when we were dealing with the
I think it's because we assume they are real value functions.
Sorry, can you say it louder?
Because I think if either one is 0, then we have complex value functions.
Is either one to be what? To be 0?
No, either one. There has to be at least one of the partial x or partial y to be complex valued.
Sorry, I still don't get that comment. Do you mind say it and try to reformulate that?
It's like if we let any bracket to equal to 0, we need to have either partial x or partial y equals to some complex value function.
But that's not a question, right? Because I mean, so before we really solve the problem, we cannot assume that the solution is completely real or completely complex. That's not. I don't think that's going to be most of the problem. Okay. So indeed, by doing something like this, then you will be obtaining something like, okay, so ux plus iuy, okay, equals to 0, and ux minus iuy equals to 0. So this is a useful exercise for those. Okay? If you are interested in, and if you have too much time to, then you don't know how to spend. Okay, this is probably a good way for you to do it. So proceed. You can proceed. Try to proceed with this. and see what we're going to get. Okay, and see what we're going to get. Especially under, you don't have to be restricted with the boundary at the very beginning. Okay, you could assume, like when we were first dealing with the wave equation, assume that the solution exists in all in the whole plane. Okay, and then see what will happen. Okay, so and then after that, if you could successfully obtain the solution, then you can come back. Okay, and actually I don't doubt that you're going to use successfully obtain a solution for this. Okay, and then you can come back. Okay, to see what is the best way. Okay, for you to carry out the solution. Can you still use that? Okay, within the box. And the answer is that well, not quite so. Okay, but anyway, so this is a drawing back. Okay, this is a drawing back to what we have learned before. But over here, you see, the if we are not using the factorization, but instead using the separation of variables, okay, which is the Will solution provided by the book. Then, well, it's actually pretty standard for us to how to proceed. Right? It's actually pretty standard for us to how to proceed. So, does anyone want to know how to move on? Can anyone tell me how to move on? If we would like to do separation of a wheel. First of all, what to assume? Assuming my u r theta to be what? Okay, R, and then theta. Okay, and then put it back. Okay, to our PDE. Then we will be obtaining something like R prime prime theta. Okay, and then plus 1 over R prime theta, and then plus 1 over R squared R theta prime prime, which equals to 0. Okay, and then of course let's first divide the whole equation with R multiplied by theta. So the both sides 1 over R theta, okay, is still 0. And then we'll be having something like R prime prime over R plus 1 over R prime over R, and then plus, okay, and then plus 1 over R squared, okay, 1 over R squared, let's say theta prime prime over theta equals to 0. How do you propose to proceed over here? Because clearly, I mean, it's not a constant. It's not a constant, right? So it's not as trivial as before. That R prime prime over R is just a constant. R prime over R is a constant. No, that's not going to work anymore. Okay. So how do you propose to proceed?
Multiply R squared on both sides and we get.
Sorry?
We times R squared on both sides.
Why do you, okay, so can you just give me a reason? Why do you want to multiply R squared on both sides?
Because as long as the function involves big R and small r, that it is a single valued function.
That's right? Because you see, if I multiply R squared on both sides, if I multiply R squared on both sides, then what we have is actually R squared, R prime prime over R, and then plus R prime over R, okay, and then plus theta prime prime over theta equals to 0. Now what can we claim? What can we claim?
They're constants.
Again, R prime prime is a function of what? R. R squared is a function of R. R is a function of R. So this is a function of R. This is a function of R. This is a function of theta. So the sum of these two guys are what? Function of R. And this is a function of theta. Again, their sum is 0. So what happens again? What happens again? What happens again?
Constant.
This is at most a constant. This is at most a constant. Okay. So now we can safely say that. Okay. So theta prime prime over theta. okay, equals to, let's say, negative lambda, and then my r squared, r prime prime, over r, and then plus r square, small r, big R prime, and the big R is negative number, it's positive number. Okay, it's positive number. Okay, again, question. We have a negative number over here, we have a positive number over here. Which one can be positive? Which one can be negative? Or they should both be zero? Theta is what? Theta is what? Theta is what kind of function? Periodic function.
Periodic.
So here actually we're looking for what? We're looking for the eigenvalue and eigenfunctions for the second order differential operator. And this time we're doing that in what space? In periodic space. Okay. So that's actually the problem. This is actually the Fourier series. Okay. From many pi to pi, equipped with what kind of boundary? Equipped with what kind of boundary? Boundary condition? Periodic boundary condition. Periodic boundary condition. Right? So it tells us that, okay, and periodic boundary conditions, what kind of boundary condition? Symmetric. This is symmetric. This is symmetric boundary condition. It's a symmetric boundary condition which tells us that this number, this negative number, okay, and this number, the number over here can only be positive. Okay. Oh, sorry, it can only be non-negative. Right, it can only be non-negative. And therefore, here, this positive number here, this guy has to be non-negative. Okay? So that means that, and what's more? Okay, what's more? For theta prime prime over theta, which equals to negative number, and we are talking about, so which means that we're talking about solutions like, okay, theta. Let's say so. Okay, so according to our knowledge of the Fourier series for periodic for periodic space. Okay, now we can say that the number can only equals to n squared. Okay, and my sorry, let me use this. Okay, my theta, this guy can only equals to a n cosine n theta, and then plus b n sine n theta. For my n equals to 1, 2, but there's another specific choice for n equals to 0, which means that equals to a0. So it's good because it's also okay. It's also okay for my lambda equals to 0 and my theta is a constant. Right, my theta is a constant function, not necessarily a constant function. So and so now you see my lambda n, okay, my lambda n equals to n squared. So now what we're having is r squared, okay, r prime prime, okay, and then plus r squared, r prime, and then minus, okay, n squared r equals to 0. Again, r is a function of r. Okay? Big R is a function of small. Okay? This is what, again, a second order ODE. Do you want to spend a few minutes to solve that? Yes. So, because this is because only when n is an integer, the sine n theta and cosine theta will be periodic from 0 up to 2. Well, actually, you know what? Actually, you can to facilitate your solution, let's say we are only considering R okay, equals to R the alpha times. R the alpha times. Just consider this type of, I'm not saying that there's absolutely no other type of equations, but actually, in fact, actually there is only this type of solutions to R, but assuming that we already know this, now we can proceed. Oh, sorry, there's no R squared in the second, for the second coefficient, right? Okay, I'm sorry about that, there's only R over here. So, if you put it back, okay, if you put this assumption, okay, to over here, then what you are going to see is that you will be obtaining, okay, so alpha minus 1 r the n times, and then plus alpha, r the alpha times, and then plus alpha r the alpha times, and then minus n squared r the alpha times, which equals to 0. Right? This is what we are going to see. This is what we're going to see. Well, of course, in this case, your alpha should not be 1. Right? Your alpha should not be 1. If your alpha is 1, then actually that means that the second order derivative of alpha of r the 1 times is actually going to be 0. But here it suggests that well, you know what? R the alpha equals to 1. It's actually okay. It doesn't matter. Okay. It's actually okay in this case. Okay, so now what we are having is that, okay, now you see I'm having a R the alpha times, R the alpha times, R the alpha times, so we're actually having alpha squared minus alpha plus alpha and minus n squared equals to 0. So it's basically R alpha squared equals to n squared. Okay, so it tells me that alpha equals to plus minus n. Okay, alpha equals to plus minus n. And what does it tell me for my RR? What does it tell me for my RR? What does it tell me for my RR? So let's say this is my theta n theta. Okay, Rn. Yes. Okay. So here my Rn R actually equals to C. Okay, Cn R the n times plus Pn R the negative n times. This is because both R the n times and R negative n times are solutions, okay, to this equation, and according to that, this is the linear ODE. Okay, we should do a linear combination of all the possible choices. Okay, so now we can safely say that U R theta, actually it should be what, right? It should be summing up, okay? So n starting from 1 to infinity, okay? N starting from let's say n starting from 1 to infinity. So let me not do the sum right away. Okay. So now let me say, what is my UN? Okay, my UN R theta is exactly Rn R multiplied by theta n theta, right? Okay, so this is actually Cn r to n times plus dn over r to n times, multiplied by here an cosine n theta, and then plus dn sine n theta. Sounds so good? This is my theta, n theta. This is my r n r. And my un, okay, the nth term in the nth term in the series. Okay, this can go to r and r with the theta. Okay. Okay. But this is for n equals to 1 and 2, blah blah blah. Right? What about what will happen when n equals to 0? What will happen when n equals to 0? What will happen when n equals to 0? Because you see, we successfully argued over here that for theta n theta, okay, there is a possibility for n equals to 0. In this case, the theta function is going to be a constant, okay, in the whole face, on the whole circle. Okay? So, which means that my number 0 is actually 0. Which means that here, I can produce something like n equals to 0. Right? When n equals to 0, actually we'll be facing a PDE, we'll be facing an ODE, which is r squared, okay, r0 prime prime, and then plus r0 prime equals to 0. Right? And actually we have already solved this equation. In one of our previous lectures, which means that here my r0, okay, my r0r is going to be something like, okay, c0 plus d0 log r. See, here is where log comes from, okay, c0 plus d0 r. Okay, and considering that in this case the theta 0 theta, okay, is actually a0, so the corresponding theta 0, not theta. Theta 0 theta, okay? Theta 0 theta. The theta 0 theta over here and r0 r over here, so we'll be obtaining something like u0 r theta, okay? u0 r theta actually is directly equals to something like c0 plus d0 log r. And the a0 over there can be absorbed, okay, by the c0 and d0.
Professor.
Yes.
Professor, can I ask a question? Why when n equals 0 and theta 0 is constant instead of a linear function?
Because, okay, this is because what does my theta have to satisfy? Theta prime prime is a what? So it has to be an eigenfunction.
Periodic.
It has to be an eigenfunction, right? So, you are saying that, okay. Now, okay, so I see your point. You are saying that if theta is a linear function, then theta prime prime is still 0, okay? Then my number 0 can still be 0. Is that what you're trying to say? But don't forget, what space is theta in?
It's from 0
to 2 pi, right? If that's a linear function, what will happen? If it is a non-constant linear function, what will happen? I'm talking about, let's say, from negative pi to 2 pi, right?
Oh.
Now we have something like this. This is normal periodic.
Oh.
Okay. I need something that's periodic. So yes, so this is my so this is it. Okay, but you see, this is my u0. Okay, this is my un, and we propose that we actually propose that our u r theta should be a linear combination. Okay, should be a linear combination of all the, let's say n going from 0 to infinity, all the un over here. Okay, all the un over here, un r theta over here. However, what do you say about the log r and the 1 over rn times over here? What would they do?
It's singular at the.
They are singular, right? They are exactly singular around 0.
And the singularity around 0 will make it will lead to what? Will lead to that the function is not exactly harmonic at the original point. Right? The function is not exactly harmonic at the original point. So actually, so that's to say, when we are solving this ODE, okay, when we are solving this ODE, this or this, okay, when we are solving this ODE, we actually need to add one condition. Okay, we actually need one condition. So we need to add one boundary condition at r equals to 0, which indicate the original point. Right? R equals to 0 only stands for the original point, right? We need one boundary condition at r equals to 0 such that r0, okay, has to be finite. Has to be finite. Okay, r0 has to be finite. Or let me say the absolute value, okay, the absolute value of r0. That is has to be finite. Again, if there is infinity, that means that our original point is going to be singular. Okay, which means that at this point we cannot carry out the Laplace operator. Okay, we won't be able to carry out the Laplace operator. Okay. So if we are considering the 0, okay, so if we are considering the finite boundary condition at r equals to 0, that actually rule out this and this, okay, instantly. This goes away, and this goes away. Right? Again, because this is because these different solutions, okay, of RR actually will incur, indeed, they will incur singularity or infinite boundary condition at 0. Okay, so they should be allowed. So that means that again, don't forget that my U is a linear combination of all the UN, but now the UN, the UN only includes what? When n is 0, it only includes a constant. Okay, no more the log r term. Okay, no more the log r term. As we have explained, why the log r cannot be there. And also, when n is not finite, okay, when n is not 0, then actually Cn are the nth time multiplied by an cosine n theta and b n sine n theta, right? Okay, so this means that my ur theta, okay, is written into something like C0 and then plus the sum n from 1 to infinity r the n times, okay, and then an cosine n theta, and then plus bn sine n theta. Well, actually, the Cn over here can be absorbed. The Cn over here can be absorbed, okay, into an and bn. So far so good? So far so good? Well, if we would like to be in comply with our tradition of the full Fourier series, we can also write the original term into something like 1 over 2 b0. Okay, doesn't really matter. Right? Right? Okay, so finally, how do we determine these values? How do we determine these coefficients? How do we determine these coefficients? What we haven't utilized so far.
The boundary.
The boundary condition, right? The boundary condition. And the boundary condition tells us what? The boundary condition tells us what? Okay. On the boundary, okay, when r equals to a, on the boundary, actually u equals to h theta, right? So again, it tells us that, okay, according to the boundary condition, it tells us that u a theta equals to h theta. Okay. Well, we just need to plug r equals to a to this equation. So now, this equals to 1 over 2a0 plus the sum from n to 1 to infinity, a to n times a n cosine n theta, and the plus b n sine n theta. Okay, now can you determine the coefficients now? Are you able to determine the coefficients now? Well, again, it seems not directly a Fourier synthesis, However, if we, let's say, if we are writing something like a the n times a n should be something like, let's say, we have used, really use say c, I don't really want x. So let's say, u and v is also not so good. P, okay? So Pn, okay, and a the n times Bn equals to Qn. Okay, so now this becomes something like, okay, 1 over 2 Pn and then plus sum n from 1 to infinity. Okay, Pn cosine n theta and then plus Qn sine n theta. Sorry, n theta.
P0.
Yes,
P0, the first.
P0, yes, you're right. P0. See, and this is completely a Fourier coefficient. This is a completely Fourier coefficients problem. Okay, Fourier coefficients problem. We are looking for a full Fourier series. Okay, we are looking for a full Fourier series for what? For exactly, okay, H theta. H theta is what? H theta is a periodic function, okay, defined from 0 to 2 pi or from negative pi to pi, depends on how we do it. So what's it? Okay, then we can determine P0, Pn, Qn, okay, very directly, and then from that we'll be able to deduce what is An and what is Pn through this relation. Okay, and so finally, if we would like to write it down, okay, if we would like to write it down, then we are having, An to be exactly 1 over pi, a to n times, okay, from 0 to 2 pi, h phi, okay, h phi, cosine n theta, and let's say, why don't I just use theta? Okay, h theta, cosine n theta, d theta, and then dn equals to 1 over pi, a to n times 0 from 2 pi, and then h theta, and then sine n theta, okay, n theta, and then e. This is my a and this is dn. Well, what about my a0? What about my a0? What about my a0? Well, my a0, okay, a0 is actually the same thing, right? a0 is actually here, it's actually 1 over pi, and then from 0 to 2 pi, and then h theta. Okay, theta. Because cosine 0 is 1. Cosine 0 is 1. Okay, now, again, so let me ask you a couple of questions before we get into it. What if my h theta is a constant function? What can you tell in the integral, from the integral? What if my h theta is completely a constant?
Bn is 0.
And then this integral is going to be what? 0, right? Because cosine, the integration of cosine n theta is always 0. What about this guy? Also, what? Also 0. So that's good? Okay. And then what does that lead to? That means that actually, essentially, this term doesn't exist, right? This term, these terms doesn't exist. And there's only one term, 1 over 2 a0, which is what? Which is a constant over here. And why is that? Why does that happen?
Maximum.
According to the maximum principle. We have to stress this for technical times. Okay. According to the maximum principles, because the constant, if it is a constant on the boundary, okay, then maximum, minimum, everything is the same. So constant. Okay, so and what exactly is that constant? What is exactly is that constant? So you see, if my h theta is a constant, let's say constant c, then what is this equal to? 2h. Yes, 2 pi h, and then 1 over pi, right? 2h. But there is 1 over 2 a0 over here. So indeed, okay, constant. So that means that indeed tells you that if my h theta is a constant, then the solution is exactly the constant all the time. Okay, all over the place, Okay, within the disk. And this is one thing. And another thing is that, okay, we are actually not that we're not completely satisfied. Okay, we are not actually completely satisfied with this solution. Okay, this is because we are still viewing a series solution. This is because we are still viewing a series solution. And instead, actually, there is hope. Okay, there is hope for us to further simplify it. So now let me write down. Okay, let me write down the solution. Okay, to another place. So let's say u r theta, which equals to 1/2a0, and then plus sum n from 1 to infinity are the n times a n cosine n theta, and then plus b n sine n theta. Okay, don't forget. Okay, don't forget. We already know what is a and b, right? We already know what is a and b. So just plug it in. Okay, just plug it in because it's the a and b that contain the information of the boundary vector of the boundary. Okay, but nowhere else. So this actually equals to, okay, from 0 to 2 pi, okay, h theta, d theta, 1/2 pi, okay, and then plus the sum, okay, m from 1 to infinity, okay, r the n times, pi, a the n times, okay, and from 0 to 2 pi, h theta, okay, and then I see why we need another angle. Okay, sorry, why we need another variable for the angle over here. Let's say h phi, okay, d phi, and here is h phi, and then multiply by cosine n phi, cosine n theta, and then plus sine n phi, sine n theta, d phi. Have we ever learned how to simplify this further? We have learned that in the last chapter, in the last section of Fourier series. Right, we have learned that in the last chapter of Fourier series because this is directly cosine n theta minus phi. Right, so the whole solution is actually, okay, from 0 to 2 pi, okay, and h phi multiplied by 1 plus 2, okay. Now the sum, n going from 1 to infinity, r squared over a squared, r to n times over a to n times, r to n times over a to n times, and then cosine n phi theta minus phi, okay, and then d phi over 2 pi. Still, it looks horrible. It still looks horrible, but you see, when I'm summing up from 1 to infinity, r to n times over a to n times, this term is what? Is geometric. The problem is the cosine n theta minus phi. So again, our idea is that if we could introduce a geometric sequence, okay, to finish our job. Can we ever do that? Can we rewrite cosine n theta minus phi into a geometric sequence? Right? Okay, we learned that exactly in 5.5, at the beginning of 5.5. That belongs to the step number 1 when we were trying to prove the pointwise convergence. Okay, the pointwise convergence of the Fourier series. Okay. What is that? Well, we just needed to write cosine n theta minus phi, right, into either I n theta minus phi, okay, and then plus either negative I n theta minus phi, okay, and over 2. Just in that. Okay.
So by doing that, we are essentially, we are essentially. So actually, let me try to compute the flower bracket, separately. Okay, so this actually equals to 1 plus the sum m from 1 to infinity, r the n times over a the n times, and cosine n, cosine n theta minus phi, right? And at the same time, this actually equals to, 1 plus actually the sum m from 1 to infinity, r the n times over a the n times, e the I n theta minus phi, and then plus m from, there's a 2 here, m from 1 to infinity, r the n times over a the n times, and then e the negative I n theta minus phi. Right, and then we can just deal with that separately. And then finally, we'll have something like 1 plus r e the I, theta minus phi. And then over a minus r e the I theta minus phi, and then plus r e the I theta minus phi, negative minus phi, and then a minus r e the negative I theta minus phi. So and by summing up, so again, this is the outcome of a geometric sequence. This is the outcome of another geometric sequence. And then finally, we obtain something like a squared minus r squared over a squared minus 2ar, cosine theta minus phi plus r squared. And which means that my, don't forget, this is where my ur theta comes from, right? So, which means that finally my ur theta, this guy actually equals to a squared minus r squared, because this is a common factor. This is a common factor, and coming out, and multiply from the integration from 0 to 2 pi, and then here h phi will come out. H phi will still be there. H phi over here, the a squared minus 2ar cosine theta minus phi, and then plus r squared, and then d phi over 2 pi. And this is the so-called Poisson's formula. This is so-called Poisson's formula. For Laplace equation. This is the Poisson's formula for Laplace equation. It reviews how the solution, directly depends on the Dirichlet boundary condition H phi over here. And why don't we take a 5 minutes break for now? And then we'll be resuming on 3:30.
你选儿。
没。
它那个之前那个log r 和那个 sin r 乘上 dn over r 那个是怎么变成一个常数了是吗？还是咋？
不是变常数就直接消失了，就这一项不存在。
他是说啥不存在？
因为你需要让它的那个 origin 是，因为你如果它这两个任意一个是不等于0的话，你这个 origin 就是 singular 的，所以说你只能把它们两个相当于是这两项。因为你不管怎么样，你把它挪掉，它也是满足这个 function 的，它本来它也是 linear combination 出来的，所以你说它不是 singular，所以这两项就全都是0了。拿掉没有？
对，他说，不，如果这两项存在是一个什么情况？ 存在的话就是它
就是
是无
任
非那个
意一
是，
项存在，
它是在
它都
零的时候它是
不能不能满足这个，
为啥必须要满足这个来着？
它是设置的 boundary condition，只是它额外加的一个，它如果不加那
OK，
因为
他没说为啥
它不是，其实也不是额外加的，因为你在整个整个这个圆里边都是 harmonic 的，然后你这一点上如果 singular，它就肯定不是 harmonic，就是在 origin。
这个地方这边常数，OK，这边常数，行。啊，是为了要在那个整个那个圆里面都是 harmonic。
对对对。
所以，
Wait, where does the natural log of r come? Oh, okay. I see.
OK，是这样的话吗？就是 OK，这边常数 OK。
What does this mean? You are multiplied by what is that singular r? So no, that doesn't make sense.
Because so this one becomes ln r u r.
Are you trying to? Are you suggesting something like 1 plus natural log of r, and then r, and then u, and then r?
Yeah. So I guess it's backwards.
You're suggesting something like 1 plus natural log of r, u, and then r. You're suggesting this, right?
Yes. And then the other term is the same.
Sit up.
It's 1 over r squared. 1 over r squared.
Oops.
And then this you can definitely back.
I'm not quite sure. But let's see. Let's see what is the next step.
I just said square root.
Square root.
Using this same idea
No.
here.
No. Because when you are doing, okay, so let's suppose you see that was first. So you're proposing u zeta, and then plus I square root of I plus natural log of r u r. Okay, u r, and then the other one is the minus. Right? But you see the problem is that. Sorry, actually, what I should do is not u r here. This is actually deceptive.
Yeah.
So actually, what I should really do is do partial zeta, and then partial r, and then partial r, and then partial zeta, right? And you see, what's the problem? The problem is that, so when I'm doing this and this, right, the partial r is also going to action upon 1 plus natural log of r, square root of 1 plus natural log of r. See? So this will not exactly produce this.
But doesn't the term cancel? Doesn't the middle term cancel?
Yes, the medium, no, wait a minute.
Because they're identical.
Oh, yes, okay, the auxiliary term will cancel, I agree. The auxiliary term will cancel, but the problem is that now, this term will not be exactly different. Because you are, okay, so let me call this factor something like AR. So what you are asking for, something like partial R, AR, okay, AR, and then partial R, AR, and then partial R, you're asking for this. See, you're asking for this. So now when you're doing the differentiation, of course, there's going to be a term to be AR, partial R, R, U, and then AR comes out squared, but there's going to be another term which is R, okay, and then a prime R, and partial R as well.
So what this term is going to be 1 over r, right?
No, because you are going to use it up. You are going to use it up. See?
And the square root of 2.
Yeah.
Okay.
Yeah.
I was close.
That's a nice one.
Okay, so let's try to resume. There is actually, I mean, you see, this Poisson's formula is seems a little bit, it seems a little bit, well, how to put it, still very, sorry. This Poisson's formula still seems very hard to memorize, okay? But there's actually one way for us to further simplify it, okay? Which is that, now you see, we have still been trying to, we have all of our efforts, okay, belongs to the polar coordinates. This was actually very natural because, you see, the whole boundary was a circle. It was actually natural for us to consider for a polar coordinate. But the most problematic stuff, perhaps the most problematic stuff, is this, is the denominator in the integral. Right? It's the denominator in the integral. And so we wonder if there is a way, okay, to further simplify what we're having over here. So what we are exactly having is that, okay, so we would like to further simplify what we call, what we have been calling as a squared minus a 2ar cosine theta minus phi plus r squared. Okay, so we have been asking for this. So now you see, but you see, what is exactly that exactly that we are looking into? I mean, let us try to make a geometrical figure here. So you see, we are having, let's say, we're actually looking into two different points. We're actually looking into two different points. One point has a polar coordinate as a, okay, a theta. Or actually, let's say a phi. Okay. Let's say a phi. And another one has a polar coordinate as r theta. Right? This is the we're looking into a theta. We're looking into a phi and r theta. So since everything is exactly okay in the polar coordinate, and let's just say this is my circle. Okay, this is my circle. So my a phi is over here. Okay, this is 0. This is 0. And this is my a phi. This point is exactly my a phi. And my r theta lies within the circle. So it lies within the unit disk. So my r theta is over here. Okay? This is my r theta. So let's first try to see what will happen if my theta minus phi is an exact angle. Okay. What if my theta minus phi is an exact angle, which means that if my theta minus phi exactly equals to 2 pi, sorry, pi over 2. Is exactly equals to pi over 2, or negative pi over 2. Let's see what will happen in this case. Okay? So if that happens, then that means that I'm actually looking into something like this. Okay, this is actually my r theta. This is actually my r theta, and here we're having exact angle. Okay. Now, what can I say about a squared minus 2ar cosine phi minus theta and plus r squared?
Cosine.
When my theta minus phi equals to pi over 2 or negative pi over 2, what is my cosine?
Oh, 0.
What is my cosine? 0. Right. So this is actually what? A squared plus r squared. If this is a, this is r, what is a squared plus r squared?
What's the distance?
Okay? It's the distances between them, right? It's the distances between them. So that's
Oh.
good.
喂，
哦，
So that's good.
Yeah.
Now,
余
if
弦
my
余
theta
余弦
exactly equals to pi, equals to phi, what will happen?
哦
If my theta exactly equals to phi, what will happen?
，it's
Okay, cosine 0 is going to be 1.
1
So this is going to be a squared minus 2ar plus r squared. What is exactly that? A squared minus 2ar plus r squared, that's actually a minus r squared in this case. In this
Oh.
case,
it's
the
it's
r theta is actually here, right? Because theta is the phi. So this is going to be,
it's the square of the distance.
yes,
Okay,
that's again the distances between these two things.
the square
Okay,
of
one
the
more example, one more example. What if theta minus phi is exactly pi? Which means that they are exactly
This is
on the opposite
on the
angles.
other side.
Opposite angles. So in this case, for cosine pi, actually that's going to be negative 1. So this is going to be a squared plus 2ar plus r squared. So the whole thing is going to be what? Okay, the whole thing is
plus r.
actually going to be a
Bracket.
plus r squared, and in this case, we're actually talking about this. See, so we have a very solid reason to suspect that this actually equals to, okay, x minus x prime squared, where my x is exactly, okay, has a polar coordinate, where my x exactly has a polar coordinate, ar, and my x prime exactly have a polar coordinate. And my bad. So actually here has a polar coordinate r, let's say r theta, and x prime a phi. Okay? And actually, it's not very hard. Okay. It's actually not very hard to obtain that if I'm having a triangle. Okay, one side of it is a, another side of it is r. Okay, and their angle is actually theta. And how do you compute the length of the third angle? I'm sorry, the third side. It's actually exactly, okay, it's actually exactly the square root of a squared, okay, plus r
Plus
squared,
r squared
and then minus
minus
2ar
2ar
cosine.
cosine.
Okay, theta. Cosine theta. It's actually, you can directly compute it. So actually, that means that if we are turning everything back into the Cartesian coordinate, okay, if we are turning everything back into the Cartesian coordinate, that means that, okay, my u x vector, okay, exactly equals to a squared. Well, what is r squared? Well, a squared, we already know what is a, because it's fixed all the time, but what is r squared? R squared is actually x squared, right?
Oh, x squared.
Over 2 pi a. And then, now, this integral takes place when my x prime, okay, is on the circle, is on the circle with the radius a. And then, this is going to be u x prime, okay, over x minus x prime squared, and then ds prime. Okay, and what is s prime? S prime is the S prime is a infinite small arc, okay, on the circle. It's an infinite small arc on the circle.
U.
So what does this remind you? What does this remind you? Okay, this is the solution. The solution is expressed in an integral. Okay, this is not so unexpected. But you see here, the important thing is that we're having something that's, okay, x, which is fixed in this case because we're looking for the solution at the point x, but also an x prime, okay, which in this case are going over all the circle. What does that remind you? What does that remind you? Convolution, right? It's not exactly a convolution, but it looks like it. But it actually has the form, has a very similar form of the convolution. It's not exactly a convolution, but it's actually close to the form of a convolution. Because in a convolution, we are also fixing what? We're also fixing x, fixing one thing, okay? And then, right, do the other thing, right? So it's actually not so hard, okay? It's actually not so hard to relate this to the convolution. So when was the last time that we were facing convolution? That was the source function, right? The source function of the heat equation. So in this case, okay, this is not a source function. This is not exactly the source function for us. But you see, this actually depends on what? This actually, first of all, we rely on the boundary condition, okay, and we are performing a linear transform, okay, for the boundary condition to obtain the boundary condition on x prime or x prime on the circle A, okay, to obtain the function value for all other places, okay, and by doing that, we are actually relying on we are actually relying on the difference, okay, between these 2 points. We're actually relying on the difference between these 2 points. Therefore, this is actually not so hard for us to remind us the convolution and the convolution and therefore the idea of convolution and the source function. This is actually called the Green's function. Okay? This is actually called the Green's function. This is actually called the Green's function, and we will actually discuss that very quickly, okay, in chapter 7. What we are talking about. So again, the idea of the Green's function is exactly the same as the source function, which is that now we are having the initial condition or the boundary condition, whatever it is, right? We're having this initial condition or its surrogate or its analog. Then how do we impose the linear transform, okay, on the initial condition to obtain the solution in the other places? To obtain the solution in other places. And also, the source, what does it mean by the source function? The source function means that it can be applied, okay, to every single point in within the solution, and every single point of the initial condition, okay, without any bias. Okay. So this is the idea of the Green's function or the source function, which we can discuss later, okay, in chapter 7 and chapter 12. Perhaps there's only one more. Okay, perhaps there's only one more thing for me to discuss. Okay, before we close the topic today, because I do apologize because I may need to go a little bit early because I'm feeling a little bit weird and probably not feeling so well for now. Okay, sorry about that. So the last thing, but I suppose I will be able to hold on to it until the class is dismissed. Okay, so the last thing that we'd like to discuss is the mean value property. Okay, the last thing that we need to discuss is the mean value property. And actually, this actually directly comes from these 2 things. Okay, this actually directly comes from either the 2 forms, okay, either of the 2 forms of the solution. So let's say what would happen if I'm talking about U0 setup. Well, in this case, we're talking about the solution at the original point. Okay, and the setup doesn't matter. What will happen in this case? What will happen in this case?
It's 0.
What will happen in this case? Okay, we can start from here. When I'm always staying at 0, then the norm
Of
of x is always going to be
zero.
0. Right? So the first term is actually becoming, okay, a squared over 2 pi a. What about the second one? What about the second one? Well, again, we are still integrating on the circle A. So x prime, okay, equals to a, but it's now becoming u x, okay, and over what? What is x minus x prime? What is the square of x minus x prime? X is a point at which place?
It's,
X-
it's at the origin,
X is at the original point. X prime is at which place?
at the boundary.
Is on the circle. So, which means that x minus x prime is always what? Okay, the norm is always what? The norm is always a, right? The norm is actually always a. So it's actually a squared over here and then ds. So one more thing to do is actually we can put it out. 1 over 2 pi a, the integration x prime equals to a ux prime ds. What is this?
Professor, can I ask a question? So for the Green's function, why is there an additional a in the denominator?
There is no additional a.
No, in the
Denominator 2 pi
2
a.
pi a.
2 pi a,
Why
yeah.
do we add an a to the denominator? Because
probably
it's
2
not
pi.
it's not
有这个 a，因为 SP 是 a。
Oh.
is there any relationship between?
This is because let me tell you why it's that. This is
Oh.
because the integration converts, okay, on the circle a. Okay, which means that if the a is smaller, then the whole integrand becomes smaller. If a is larger, the whole integrand becomes larger. Right? Which means that the outcome, okay, the outcome of this will actually contain a factor of a. The outcome of the integral will contain a factor of a, which means it has to be cancelled by another a over here. Is that okay?
And is S prime the arc length of the
Yes. So more specifically, it depends on how large is the ds prime over here. You see, so this is like this, right? So I'm having a large circle and I'm having a small circle. Now I'm doing a very small differentiation of theta. Okay. Here, this is my ds1. This is my ds2. Right? Okay. Of course, the differentiation of the arcs is related to what? It's related to a. It's related
So
to-
in the
radius.
formula d S prime over a is equals to d theta.
Yeah.
Oh.
Okay. So now coming back to this, what does this remind you? Well, what is this exactly? This is what? This is ux prime is the function of u on the boundary. And this integration tells you that now I'm just simply going around this boundary. I'm actually going around this boundary. Starts with it. Okay. And then doing the integration. But I'm doing what? What is the factor? What is the factor? Why do I have a factor over here? 1 over 2 pi a. What's actually 1 over 2 pi a? What is 1 over 2 pi a for a circle A?
The length of the
The length of the whole circle, right? See, so this is what? This is what? This directly tells you that the function value of u at the original point is exactly the mean value of what it is.
mean value of the
Oh, okay.
boundary.
Is exactly what it is on the boundary. Again, what will happen if my ux is a constant on the boundary? If my ux is a constant on the boundary, what will happen?
It's constant.
This means that I am integrating a constant on the whole circle. And how long is that circle? The circle is 2 pi a, so I divided everything by 2 pi a. I got the constant. I got the mean value. Okay. So now this tells you that this is the mean value property. It tells you that, okay, here, step one is that, okay, the u0 theta, okay, is the mean value. The mean value, okay, is the mean value of of the boundary. Mean value of the function u on the boundary. Okay, this is step number one. But this is far from the end of it. We're actually going to come up with much more interesting argument starting from here. Okay, so this is my step number one. So you see again, same setup. Okay, I'm having a circle. Okay, I'm having a circle, and everything stays the same. And we already know that the center. Okay, the center is exactly the original point is exactly the mean value. Okay, of the boundary. Right. Now I'm asking that if I am talking about here, a point here, not exactly as a circle, and let me draw a circle over here, what can you say?
Oh my god.
What can you say?
Wait, what is?
I'm having a red point over here, not exactly at the original point. And I am having a circle over here around this center okay, at the red point, but still strictly contained by the original circle. What can you say?
I think it's still the average value.
Why is that? Why is it still the mean value?
Okay, we can.
Why is the same? Why it is the same? We just need to
翻译
do
翻
a
上面吧，看看
spatial translation. Right? We just need to do a spatial translation.
Oh, okay.
Now, suppose that I am moving.
2派
Suppose that I am now moving the coordinate to this place. Okay? I'm now moving the coordinate to this place. And let's forget about the original boundary. We have already solved the problem. We have already know exactly what is the function value of u within the circle. So we already know what is exactly on the red circle. Okay? Well, now the blue circle. We already know exactly what it is on the blue circle. Now let's pretend we are doing the boundary value problem again using the new circle and the new coordinate. What do you say? Will we obtain exactly the same thing, right? Will we obtain exactly the same thing? This is because of the uniqueness of the solution. If it exists, it is unique. Okay. This is because of the uniqueness of the solution. So we'll be obtaining exactly the same solution as the original one. And the new solution, well, should satisfy what? The new solution should satisfy whatever we have currently in step one, because this is the new solution is centered at the new dot, red dots, with the new circle. So we can still argue that. Step number two. Okay, step number two. U r theta, as long as my r is smaller than a, okay, is the mean value of u on a circle. On a circle, okay, on a circle surrounding it. Okay, centered at. Centered, okay, at r theta. Okay, this actually holds. Okay, as long as the circle is still within circle A. Right, still within circle A. That actually works for arbitrary point and arbitrary circle as long as the circle is confined by the original circle A. Okay. Sounds good? Sounds good? Yes.
Does it necessarily need to be a circle? Or how about that?
You're very sharp. It doesn't have to.
Oh.
Okay. It doesn't have to.
Wait.
Actually, this is exactly the next thing I would like to propose to you, which is that how do I put it? Actually, I cannot exactly remember the way that we put it, but you can obtain a similar form of the mean value. Okay, as long as everything, as long as we are still within the domain. Okay, or let me put it this way. Okay, let me put it this way. So now let's say I am having okay, I'm having something like this. Okay, I'm having something like this, and I'm having a point over here. Okay, I'm having a point over here. Okay, then again, I'm trying to solve a Dirichlet. I'm trying to solve a Dirichlet boundary problem, right? Okay. Then you will be expecting the things is that you will be expecting something exactly as this. You will be expecting something exactly as this. Okay, not exactly like a circle, but still in the sense that we'll only be first relying on the values on the boundary, okay, and then second, how far is it away from the boundary? Okay, so ux means the value on the boundary, and x minus x prime means how far it is away from the boundary, from the point on the boundary. Okay, you will be obtaining. So why the Poisson's formula is important is that actually this can be migrated, okay, to an arbitrary boundary. And how to do that? Actually, we don't have time to get into detail, but you can imagine the following. I first draw a circle as large as I could do, okay, which centers at the backwards. And then I fill in the gap with more circles, with more circles, with more circles. Every time, and the new circles should be exactly adjacent, okay, to the old circle. Okay. And in this way, okay, we will be able to expand the boundary, okay, more and more and more and more and more and more. So you will get close. So you will actually absorb it. So which means that these circles, okay, will be able to coincide with the boundary. Okay, more and more points, more and more points, more and more points, more and more points. And if you continue to do this process, you will be able to touch the boundary on every single point. Okay. In this, and you can do that in that way. Okay. And by doing that, you'll be able to project, okay, all of the boundary values, okay, to the black dots to represent the black dots. So another way to put this. So there's another way to put it. Okay. The mean value property tells you. The mean value property tells you that, okay, if I am a harmonic function, then that means that, okay, I will be exactly the mean value of a circle centered at me, of the values on the circle centered at me. If I'm not talking about an exact circle. If I'm talking about an arbitrary shape surrounding me, then it's not going to be the exact mean value. It's going to be what? It's going to be a weighted average. It's going to be a weighted average. Okay? And so step number 3. Step number 3. Okay. If the boundary is not an exact circle, okay, then the mean value is replaced by a weighted average. Okay, is actually replaced by a weighted average. What do you want to make a guess? What does the weight depend on?
Depend on the
The
distance between
the
the.
exact distance. Okay. The weight depends on the distance, and the weight, okay, depends on the distance to the boundary point. That's it. So this is the so-called the mean value property. Okay, the so-called mean value property. See, so this is the amazing property held by the harmonic functions, okay, which means that if you know the boundary, okay, no matter what boundary that you know, as long as it is the Dirichlet type of boundary, which means that you know exactly what's taking place on the boundary. The u value exactly on the boundary. Then you will be able to deduce using a linear combination, or more exactly, using a weighted average, okay, to produce everything in the middle. So now we will now this is actually another way to reiterate, reiterate the maximal, the minimum, the maximum and minimum principles, right? Why the maximum and minimums are only taking place on the boundary? This is because anything interior are what? Are weighted average of the boundary values. Okay. Everything in the interior are weighted average of the boundary values. So, last comment. Okay. Y maximum and minimum principles. This is because okay, everything interior, okay, are weighted average. Average of boundary variables, boundary ones. So this is the important idea about harmonic functions. Okay, so I'm afraid I have to stop today because I still owe you 10 minutes. I do apologize for that. But, my condition now is not so good for me to continue. Okay, so sorry about that. And let's meet again this Wednesday. Okay, and then we have successfully covered everything that I would like to talk about in chapter 6.4. And yes, so that's everything that I would like to say. And there's one more thing about the proof of the limit. Okay, to tell you that indeed, okay, these two Poisson's formulas are indeed presenting a solution. But I am afraid this is not so much of our interest, especially after we have proved so many limits. Okay, we have proved for so many limits. Okay, in this class. So again, you can read it if you wish, but that's not the most important point. So this is now we have already finished. I have already finished everything is required for this course. Okay, which is from chapter 1 to chapter 6. Now the rest of the 4 course, I would like to delve into again chapter 7 and chapter 12. Okay, so we may not be able to cover everything, but I still hope I will be able to provide you most important ideas about Poisson's equations, Laplace equations in multi-dimensional space, and the Green's function, the idea of the Green's function, delta function, transform, and distributions, okay, which will rightfully record everything that we have learned for the linear partial differential equations. This is my plan for the rest of the 4 classes. Okay, I will see you all on Wednesday.因为原来